All right, so a little bit of this at the beginning is from 6.3, which is proportions. We talked a little bit about this when we were in section 7.1, kind of beginning the hypothesis testing procedures. So we're going to do a little bit of that section first, just to kind of give you some background information that you need for the proportions, and then we're going to jump to 7.4, the actual hypothesis testing part that you're going to be doing with this. All right, so first definition is a point estimate for P. P itself is a population parameter, so it's important to remember that. It is a population proportion, so when we actually get to the hypothesis testing and the confidence intervals, that's what we're going to be estimating here, is a population proportion P. So it's no longer going to be the mu, the mean, it's all going to be P's in these problems. And P hat is how we say that with the little kind of caret above it, is the sample proportion that estimates that population proportion. To calculate it, we do X, which is number of successes, divided by N, which is your sample size. So sometimes they'll give you the sample proportion and sometimes you'll have to calculate it, which really it's just a percentage of the number of successes or trials or whatever divided by the sample size. We also have something called Q hat. Q hat is the complement of P hat, so 1 minus. So it's really your probability of failure then versus the probability of success, which is what P is. All right, so at the bottom here is an example of just finding that P hat value. It says in a survey of 1,550 US adults, 1,054 said that they used the social media website Facebook. Find a point estimate for the population proportion of US adults who use Facebook. So P hat is the number of successes, or in this case, the number of yeses to people that use Facebook, which is 1,054. Divided by your sample size, which is 1,550, and we divide. And you can write this as a decimal or a percent. Most of the time I would say it's going to be decimals. You should get 0.68 is your sample proportion. Okay, so what would Q hat be then? Q hat is the complement of P hat, so Annie? 0.32. Good. Okay. Another thing that's on the next slide, we're going to come back to this problem in a second. Before we actually find hypothesis testing or confidence intervals, there's some conditions we have to check at the beginning here. You need to determine if n times p hat and n times q hat are both greater than or equal to 5. So that's figuring out if, or verifying that you have a normal distribution. We do it that way with proportions. We multiply by n, both of these values, and we check that it's greater than or equal to 5. So if I wanted to verify that this set of values would be done with a normal distribution, I would multiply my n, which my n here is 1,550, by both my p hat and my q hat, and I just need to make sure that it's greater than or equal to 5. So 1,550 times 0.68 and 1,550 times 0.32. Now when I multiply it by 0.68, we're going to get a number that we already know, 1,054, the number of people that said yeses to that survey, and 1,550 times 0.32 would be the other group, the people that said no, 496. Both of those values are greater than or equal to 5, so this can be represented with a normal distribution, which then tells us, okay, great, now you can go ahead and do those confidence intervals and that hypothesis testing. Okay. Questions there? No? Okay. So next, we are going to find a confidence interval with a proportion. So remember, we're not estimating a mean this time, we're estimating a proportion, P. And to find P, we're going to take P hat, the sample proportion, and we're going to add and subtract on that margin of error. So really similar to what we did with the mean before, but you've got a new margin of error formula now when we do proportions. We're going to find the critical value on our z-chart. So we're still finding z's. That's not going to be new. But then we're going to multiply that by the square root of p hat times q hat over n. And we just talked about how to find all of those things. So just putting them in the formula, find E, add and subtract it to your sample, you have your confidence interval. So we're going to do one of these on the next slide, finding a confidence interval. It says the figure below is a survey of 800 U.S. adults ages 18 to 29. Construct a 99% confidence interval for the population proportion of 18 to 29-year-olds who get their news on television. We've seen problems like this before where they give you a whole set of data. You don't really need all of it. In this problem, we're just talking about people that get their news on television. So really that second bar is going to be what's important here. I'm going to go ahead and start naming all my important information. Survey of 800 U.S. adults. What's 800 in terms of my variable? It's my n, my sample size. Okay. 99% confidence interval, when we did that before, we called it a C, is 0.99. And while you're at it with that, you guys can find the critical value on your z-chart that goes along with that. So these critical values, when we did them before, these are the ones that are printed already for you on your standard normal distribution. They're at the bottom. It says critical values, find 99%. And then you're just going to find the z-score that goes along with it that they've done for you here. So 99%, you guys should be able to find the 2.575. There, okay. We will need to estimate p hat, which is your sample proportion or your sample percentage, which we are given in the chart. That's that 27%, so we're going to use 0.27. If you know p hat, you can get q hat. It's complement. What is that? .73. Yep. And then we also just want to kind of verify here that we can even do this. We're going to do n times p hat and n times q hat. And we're going to make sure that both of those are greater than or equal to 5. So we can represent this with a normal distribution. All right, so 800 times 0.27 gives me 216 for the first one. 800 times 0.73 gives me 584 for the second one. Both of those are greater than or equal to 5. We're good. Okay? All right. So now, to actually get the confidence interval, you need the margin of error. Margin of error is your z-score, your critical value, 2.575, times a big square root. The numerator in this square root is going to be your p hat and your q hat. So 0.27 and 0.73. The denominator is going to be your n. 800. Type it in. Just be really careful with this, with all the fractions and radicals and things. I got 0404. Double check you can get that number okay. Maybe use alpha y equals or an extra set of parentheses if that doesn't work. Everybody get that number all right? Yeah? No? Yes? We're okay? All right. So now to find p, to estimate p, we're going to take p hat, our sample, add and subtract that error. And that's going to give us our final answer, the confidence interval. Now you're going to get decimals a lot with these because remember we're estimating proportions, which are essentially percentages. So when we see that 0.0404, it's really about 4% is our margin of error. So that's reasonable for what we're given up here. So I'm going to take 0.27. I'm going to add on my margin of error, and that gives me 0.3104. That's going to be the right side of my confidence interval. 0.27 and subtract my margin of error, I get 0.2296. And I'm giving it a few decimal places there. You could say approximately 23% to 31%, depending on how you needed to round that, would be our confidence interval. Okay, so remember we would say with 99% confidence, we can say that the actual population proportion is between 23 and 31%. So the actual number of people that get their news on TV is approximately those percentages. It's going to be in there somewhere. Questions on that? All right. Only other thing we're going to do today is we're going to put that kind of stuff together and do a hypothesis test. We're going to do one hypothesis test today, and then you'll do one that's kind of like a warm-up tomorrow. A lot of this is the same that we've been practicing with our other hypothesis testing. So at the very beginning, we want to verify that we can do it. Before it was, do you have a sample size bigger than 30, or is it normally distributed? Now we're going to be multiplying n's, p's, n's, and q's. Once we get to the hypothesis testing, when you do this initial check here, you're going to be actually using P and Q, not P hat and Q hat. You notice that there, so maybe put a little circle there. It's not with the hats anymore, it's just with the actual population parameter. Then we're going to state the claim mathematically. We practiced that already, so your null and your alternative. Level of significance you're probably going to be given. Find the critical values. We already have, it's still our Z critical values, and you guys wrote them in on the bottom of your Z chart. So we're just going to be looking at, is it left tail, right tail, two tail, and then what's going to be that critical value or values. We're going to draw the rejection regions. This one's a little bit different than what we were doing before for Z-scores because it's proportions. Maybe circle that on your paper. So we're still doing the sample minus the population on top. But the denominator is just a little bit different because we calculate that margin of error a little bit differently. But once we get the Z-score, we're going to compare it to our rejection region. If you're in the rejection region, you reject. If you're not in the rejection region, you don't reject. And then we summarize from there. All right, so let's try one of these. Let's see what this looks like. A researcher claims that less than 45% of U.S. adults, bless you, use passwords that are less secure because complicated ones are too hard to remember. In a random sample of 100 adults, 41% say that they use passwords that are less secure because complicated ones are too hard to remember. At a level of significance of 0.01, is there enough evidence to support the researcher's claim? All right, so let's name our important variables first. Can you tell me N? 100. Can you tell me P? Now, when we say P, P is the population proportion. So this is the value that would show up in your claim, in your hypotheses. What is P? 0.45. And then what is P hat, the sample proportion? 0.41. Okay. In the hypothesis testing, we're not going to use Q hat. We're instead just going to use Q. Q is the complement of P. So if P is 0.45, what's Q? 0.55. We also had a level of significance of 0.01. That's pretty much all of our stuff out of there. Okay, so let's make sure that this can be modeled with the normal distribution. We're going to do N times P and N times Q, and we're going to double check that both of those are bigger than 5 or equal to 5. So 100 times 0.45, 100 times 0.55, which, nice, pretty easy math there, is 45, and 55. Both of those are greater than or equal to 5. Check. Okay. Now our claim. Is the claim in this problem the null or the alternative? It's going to be if it's just less than, not equal to, the alternative. It's got to be equal to if it's the null. So the alternative is that, now be careful here, we're so used to writing mean there. It's a P. P is less than 0.45. Okay. And then the null that we'll be testing is P greater than or equal to 0.45. Is this going to be a left tail, a right tail, or a two-tail test? Which one do you look at? You look at the alternative. So if the alternative is less than, it is left tail. Let's find our critical value of z on your chart. Okay, so I want you guys to find your level of significance, 0.01. It's a left tail test, so you guys should see negative 2.33 on there. Everybody got it? These are the ones you wrote in we're looking at. You don't have to look at the big chart. Okay. All right, so let's draw it. Left tail test, which means my rejection region's to the left. Critical value, negative 2.33. All right, so now let's find our z-score from our sample, and we're going to figure out if it's in that rejection region or not. So to get our z, we're going to do on top, like we've always done, the sample minus the population. So p hat, 0.41, minus p, 0.45. And then this denominator just looks a little bit different. We're going to do p times q, 0.45 times 0.55, all over this, my sample size under the square root there, which is 100. Type it in your calculator. 2 decimal places would be sufficient. Again, be careful with parentheses and fractions and all the things that you need on this one. You get negative 0.80. Everybody get that number okay? All right, so is that in the rejection region? It is not. It's to the right of our rejection region. So what does that mean? Do we reject or not reject? Do not reject, or you could say fail to reject. Okay, so let's summarize. This is what we reviewed yesterday. So do we say there is enough evidence or there is not enough evidence? Okay, there is not enough evidence to, do we use the word support or reject here? We use the word support because the claim is the alternative. It's all about which one is the claim. The claim is the alternative, so you use the word support. If the claim was the null, you would use the word reject. That's that little chart we put on the board yesterday. The claim that less than 45% of U.S. adults use passwords that are less secure because complicated ones are too hard to remember. We want to make it wordy. Okay? Questions? All right, tomorrow we'll do one more of those just to practice the hypothesis testing. I'll show you how to do a couple little things in your calculator with P's, and that'll wrap it up for us. All right, so you guys have the rest of the period today to work. Your 7-3 Math Excel, as a reminder, is due tomorrow night. So be working on that. And then I think this one is due maybe like Tuesday, Wednesday next week. Got a few days on that one. All right, I'll do Cell Phone Lotto. Rest of the period is yours.